Hello everyone, my name is Magnus Madsen from Aarhus University, and today I'll tell you about relational nullable types with Boolean unification. This is joint work with Jacob van der Poel, also from Aarhus University. Let's begin by looking at some motivation. Here's a program fragment from OpenSSL written in C. We can see a comment here that says for generation, P and Q must both be null or non-null. And then we see if that is not the case, some error handling code is triggered. So what is interesting about this example is that it shows that the nullity of P somehow depends on the nullity of Q, and the nullity of Q somehow depends on the nullity of P. This is what we call relational nullability. And as I said, if this is not the case, then a runtime error may occur and this program may crash. Here is another example. This time it's a Scala program. Here we have a function called credentials provider. It takes 3 arguments, all of which are options. And then we can see it handles some of the cases. For example, the case where we have a key ID and a secret, this happens. And 2 more cases are handled. However, if we are not in one of these 3 cases, an error happens and the program will go wrong. So again, we see this pattern where apparently the nonness or sumness of these 3 parameters are interrelated. So we can ask ourselves, do such programming patterns occur in the wild? So that is where the nullity of one expression depends on the nullity of other related expressions, or if you will, the nonness or sumness of one expression depends on the nonness or sumness of other related expressions. So what we have done is we've conducted a preliminary study where we looked through GitHub code searching for code comments such as cannot both be null and similar types of documentation looking for these patterns. And what we found were, in this preliminary study, 108 programs that exhibit such programming patterns. Specifically looking at these program fragments, we make the following observations. So first, indeed this type of programming pattern does occur. Second, we see that it happens across many different languages. It happens in languages that only have null. It happens in languages that only have option, and also happens in languages that offer both. Looking at the patterns in detail, we observe that to reason about them requires both may and must information, something I will return to. And finally, we see that typically few expressions are involved. Most commonly, the nullity of one expression may depend on one other expression or maybe 2 other expressions. In rare cases, it could be up to 4 expressions that are interdependent. We also considered these programming patterns. What do they do when a case occurs that is unwanted? And the short summary is that without type system support, these programs just rely on runtime checks, often leading to crashes or exceptions and so forth. Okay, so in this work, we propose a method whereby we can capture such relational nullable programming patterns in a safe way. So the idea is that, looking back to the OpenSSL example, that we introduce a new programming construct called choose, and then you simply write the cases you're interested in, omitting any other cases. Now in this programming construct, I've written here absent and absent corresponding to null, and I've written present and present here corresponding to non-null. And again, just to repeat, you write this choose construct, and then you can omit all the cases that you're not interested in, and then the type system will enforce that this function here cannot be called with values corresponding to the missing cases. So for example, in this case, we could not invoke this function with an absent and a present value because that is not covered by the 2 cases listed here. That would be a static type error. We can do the same thing for the other example. So here we have now a function from before, takes 3 arguments. And again, we only list the cases we are interested in. The type system will then capture that these are only the 3 cases that are allowed in the type of credential provider and rule out any other attempt to call the function with any other combination other than those listed here. I will now provide an overview of our technique in just one slide. So what we do is that we propose a new calculus called lambda relational nullability that has a special pattern matching construct called choose. This construct is different from an ordinary pattern match in 3 ways. First, we can only match on nullity, so is something null or non-null. Second, we cannot nest patterns. And third, we are not required to provide all cases in the pattern match. In fact, we can leave out any number of cases and instead they will become part of the type. Okay, so how do we do this? Well, the key idea is to equip every expression in the program with two Boolean formulas, phi and psi. The first formula will track, can this expression evaluate to null or to absent? The second formula will track, well, can this expression evaluate to a non-null value or what we call present? And finally, all the types in our language are of this form. So it consists of a proper type, let's say string, and then these two Boolean formulas that track nullness and non-nullness, if you will. Okay, then we take this pattern match matrix that, remember, may not be exhaustive, and we capture its exhaustiveness condition as a Boolean formula. And finally, we take the Hindley-Milner type system, we extend it with Boolean unification, and we extend it with this choose construct. And so this gives us two important things. One is that we get parametric polymorphism. Now this just means that when I write a function that's operating on these values, well, then we can call it with values of different types. So we can call it with null in one case and non-null in another case, and so on. And second, we get principal types and complete type inference. So this means that essentially we never have to write any types. It just works out automatically. Okay, so to build some intuition, let's look at a small example. So here I have a program fragment that defines a function f. And f essentially does a pattern match on x and y. And then usually there would be 4 cases, but here we only consider 3 cases. So we consider when we have null and null, when we have null and a non-null value v, and when we have a non-null value u and a non-null value v. In other words, there's one case missing, which is if we had, say, a non-null u, comma, a null value. So we ask ourselves, what should the type of f be? Okay, well, let's assume that x and y have these types. So x has this nullable type, which consists of a proper part. Here's just pi1, but it could be string. And then let's say, for simplicity, that there's just a variable x0 that corresponds to the nullness of x, and a variable x1 that corresponds to the non-nullness of x, and similarly for y. So with that in mind, we then take the pattern match here and convert it into this matrix. Here null just gets translated to 0, and a non-null variable v gets translated into 1. Then the next step is to saturate this matrix. Essentially, it just means to simplify the matrix. So we observe that this matrix can actually become this matrix, where we have wildcards here. Then we take the matrix and we translate it into a Boolean formula, namely this one. And so this is the Boolean formula that we must demand is always true to ensure that we have exhaustiveness. So what we can do is that we can compute the most general unifier of this formula with true, and this gives us this substitution here. And then finally we can consider the type of f and apply the substitution to it, essentially yielding this function type here, which may look complicated in the beginning, but let's just take a quick look at it. So the important point here is that if we consider x1, so remember this is the non-nullness of the first argument. So if we are passed a non-null value, then this will be true. So then this part will be false. So then this part will be false. Thus the second argument cannot be null. So in other words, this type actually captures that we should not call f with a non-null value, comma, a null value. Okay, so here's the entire type system in one slide. I won't go into detail, but I do want to build some intuition. So yeah, let's just look at a few type rules. So recall that a nullable type is of this form. It consists of a proper type, and then these two Boolean formulas that capture whether the expression may evaluate to something that is null and may evaluate to something that is non-null. So when we have null, well, that can definitely evaluate to null. So we put true here, and we don't care about the rest. On the other hand, if you have a constant, I don't know, the string hello world, then that can definitely evaluate to a non-null value. So we put true here. Finally, if we have a pair then we have two typings for the subcomponents. And then the pair itself, well, that's not a null value, that is a non-null value, so we put it true here. Now, on the other hand, when we start to use values and destruct them, so for example, if we want to get the first component of a pair, well, that's where we have to be careful. We don't want to take the first component of null. That would get us stuck. So here, when we are taking the first component, we require that the type cannot be null by putting in a false. The same for second. So what this slide shows is that when we introduce values, we are careful to put true in the appropriate places, and similarly for null. And when we use values by destructing them or calling them or so on, we put false in to ensure that null does not pop up. Okay, so we have implemented this type system as an extension of the Flix programming language. In Flix, we do not have null, but we do have the option type. And so what we've done is to introduce something we call choice, which has a type parameter as option, and then it has these two Boolean formulas here called A and P. And then this data type has two constructors called absent and present, and they correspond essentially to what we've already seen. So absent is like none or like null, and present is like a non-null value or a sum value, if you will. And then using the type system and this data type, we can write combinators such as map and such as flat map, which is also known as monadic bind. And the type of flat map is actually quite interesting. So we get a function here that we're supposed to apply to the option, and then we get an option here, and then we are returning an option. Let's consider this formula here. So when can the result of such a flat map be absent? Well, looking at the code, that can happen for two reasons. One is that we're in this case, so that means that the input was absent. So that's what's captured here. So saying if the input was absent, then the result can be absent. The alternative is that the input was present, so P1 is true, but then the function actually returned us something that is absent. So that means the input was present and the function gave us something that was absent. So we get this interesting type for flat map. Okay, I also want to say that Flix is a real programming language. It has all the usual features you would expect of a functional programming language. We have a website where you can go to and learn more about it. We have a Visual Studio Code plugin. It has all the usual features. You can try out also this relational nullability in it. Finally, everything is open source and freely available. To sum up, we've discovered a new programming pattern, which we call relational nullability. The key idea is that the nullity of one expression may depend on the nullity of other related expressions. We've conducted a preliminary study of code on GitHub, and we found that such patterns do occur. And we see that reasoning about them requires both may and must information. Hence, we have these two Boolean formulas in our type system. And we also see that today programmers rely on runtime checks to enforce these invariants. So without type system support, these programs crash when things go wrong. To overcome this, we proposed a new calculus and type system, which we call lambda relational null. So this is a calculus that has a special pattern matching construct. And using this construct, you can just write a pattern match, omitting the cases that you don't want, and then the exhaustiveness condition will be captured by the type system. And specifically, this is an instance of a Hindley-Milner style type system, which we've extended with Boolean unification to automatically infer and solve these unification problems. And finally, we've proved soundness of the system. Our implementation is open source, and you can go and download it and play with it. There's a Visual Studio Code plugin, there's documentation, and so forth. Okay, thank you for your attention, and I'll now take questions.